This video is on graphing radical functions. We worked some problems in class as a warm-up, and this video was recorded after the fact. If possible, you should follow along this exploration in Desmos while you're watching and listening. So you might pause the video here and get Desmos open and set up either on your phone or on a computer. We're going to begin by looking at the table and graph of the function y equals the square root of x. We'll take a look at this other one in a minute, but I would like for you to make a table of values for y equals square root of x. Now you can use Desmos to help you with this, but we're really talking about quite a simple function here. We pick values of x, we plug them in, we get corresponding values of y. It's easy to pick 0 and say that the square root of 0 is 0. And it's easy to pick 1 and say the square root of 1 is 1. I wouldn't generally pick 2 for x in this case. Remember, if you're doing this by hand, you'll want to pick numbers for x that are easy to find the square root of, like 4, which gives you 2, or 9, which gives you 3. And so these points are on the graph of y equals the square root of x. Let's take a minute and go to Desmos and see how that will look. The graph shown here is the graph of y equals the square root of x. Notice that it's sort of a swooped shape, and the points 0, 0, 1, 1, 4, 2, and 9, 3 are all on this curve. I'd like you to take a look at what the domain of this function is. Remember that domain is all possible values of x. So when you're looking at this and you look at possible values of x, you might notice that this graph starts here. I don't really care how high it goes. For domain, I'm just looking for x values, and I notice that all of them on this curve happen when x is either 0 or some positive number. So what happened to the negatives? Why aren't there negatives in the domain of this function? Well, can we take the domain of the square root of a number? Let's take a look at the table for this function. If you put your cursor in the field where this particular one is, and I have some other ones there turned off right now, if you go to the gear and you select the table, you'll see that you get a table of values for this. And that's useful for any function. If you type in the equation, you can go to a table to complete your own table of values. I'm noticing here that my negative values of x all result in an undefined solution. Well, if you think about plugging in a number for x, we can't take the square root of a negative number or we'll get an imaginary solution. We can't plot imaginary points on a real coordinate plane. And so that part of the x values, or those possible x values, are not included in the domain of the function. In this case, our domain would have to be all x values greater than or equal to 0. Let's stop for a second with the square root and take a look just at y equals x squared. This is the graph of y equals x squared, a simple parabola. Well, if we look at that, and as in what we did in class, we graphed this line y equals x, which is the exact diagonal line. Now I want you to look at y equals the square root of x and compare it to my green parabola. For some of you, visually, you might sort of need to turn your head sideways and look at how this half of the parabola anyway, the right half, is reflected over the line y equals x, and it results in our square root function. If you think about the relationship between squaring and square rooting, You know that they're related. They're inverse operations. It makes sense that the graphs of these functions should also be related, and they are. They are a reflection over the line y equals x, as if this line was the mirror. Notice that the square root function does not reflect the left half of the parabola. We just talked about the domain of a square root function being limited to 0 and positive numbers. So there's no way for us to get the rest of this down here because the results would be a negative value, and that can't happen with a square root function. Let's do the same thing with cubed roots and cubic functions. If you recall, this orange graph is the graph of x cubed, and it's sort of that spaghetti squiggle. I'm going to leave that y equals x line up because when we graph the cubed root of x, we get, again, a reflection over this line. Now this is harder to see, but if you sort of tilt your head to the right and look, you can see that this part of the orange line is reflected here, and this part of the orange that went below the line is reflected now above the line, and the same thing happens all the way through. It's hard to do it, but if you focus on what the parent cubed root function looks like, you can see that it's sort of a sideways spaghetti squiggle, and that's the way that it should look when you're sketching the cubed root function. If you'll notice over here, this doesn't look like cubed root the way we've been writing it, with the 3 as an index and the radical symbol with an x underneath. And that's because Desmos doesn't know how to accept higher roots other than square root. But you have learned how to change those roots so that they're fraction exponents. Square root is the same as to the power of 1/2. Cubed root is the same as the power of 1/3. And this really helps us to sort of trick Desmos into graphing a cubed root function, which is what this in black here is. Let's go back to our notes and take a look at some other things now that you see a relationship. So I've added sketches of the parent function graphs for y equals the square root of x and y equals the cubed root of x. You should memorize what these look like. You can always make a table and put some points on there, but it's useful to have the basic shape memorized so you know how to start any graphing problem. We need to talk about the domain of radical functions. So we looked at the parent square root function, and we saw that the domain has to start at 0 and just include positive numbers. And that's because of the way it looks on the graph. Remember, we're looking at that sort of swoop that starts here because we can't take the square root of a negative. But what about other roots? What's the domain of the cubed root of x? Remember, that was the last one we looked at, and it was sort of the sideways spaghetti squiggle. Well, no matter how far to the left or right we went, there was some corresponding point on the graph. The domain here is all real numbers, and if you remember, we write that using an R with a double line in the beginning. So what about the fourth root of x? If you try to put in a negative number, which seems to be the thing that throws everything off, the fourth root of x also gives us a problem. Try it on your calculator. If you put in the fourth root of, let's say, -8, you'll find that you get a domain error. Well, that means it can't take the fourth root of a negative number, not just -8, but any negative number. It turns out the same thing will happen here. And you could put this into Desmos, writing x to the power of 1/4. Remember, the fourth root is the same as the power of 1/4. And see how that graph looks. The domain in this case is restricted in the same way it was for a square root function. X has to be greater than or equal to 0. So now try it for the fifth root. Again, you can use a -8 or any other negative number. If you type the fifth root of a -8 into your calculator, sure, you'll get some decimal number, but it still gives you an answer. That means it's a valid value for x. Negatives are allowed. And so we can use any real number. Now you might notice that there's sort of a pattern here. The square root uses only 0 or positives as in its domain. The cubed root is all. The fourth root is 0 and positives. And the fifth root is all. So what we'd like to do is create a general rule about the domain based on whether the root is odd or even. If you have an even root, your domain is always going to be limited to positive or 0. If you have an odd root, your domain is always going to be all real numbers. And so we can make that general statement. Now this is only if we're in sort of the parent function of that root. If we transform a function, it may change the domain. So let's take a look again at Desmos and see how this works. I have two graphs highlighted here. The red one is the parent square root function, y equals the square root of x. The green one is this one down here, the square root of x minus 3. You may notice that the green graph is just shifted right 3 from the original parent function, red graph. And if you look right here, you can see that minus 3 is happening with the x. And just like all transformations we've done for every kinds of function we've looked at through high school, you know that if it's happening to the x, it's a left or right shift. And it does the opposite of what we sort of intuitively think it will do. So minus 3 is right instead of left. How does that change the domain of this function? Well, if you look at where your possible x values are starting, they're not starting at 0 anymore. They're starting at 3, which means our domain has to be x is greater than or equal to, because everything to the right is good, 3. And so you probably could have written that, now that you know that, just by looking at this. Since it's x minus 3, instead of starting at 0, we need to start at 3. So x greater than or equal to 3 is our domain for this transformed function. So let me ask you a question. What if what's happening is not under the radical? What if it's outside of the radical? What if it's plus 3? That moved it up. Well, hasn't it always? If something isn't happening with the x in the problem, but it's sort of happening at the end, that's the up or down shift. And in this case, plus 3 moved this entire graph, up 3. Has the domain changed when there's a vertical shift up or down? It hasn't. Remember, we don't care how high something is. Domain is x. I'm only looking at the left or right, and the left and right hasn't changed. It's still starting at 0 and going to positive infinity. So x is still greater than or equal to 0 here. So basically, for the domain, you need to pay attention to what's under the radical. Anything outside of the radical will not affect the domain. I'm going to split this lesson into 2 videos because this one was largely exploring using Desmos. So we're going to start the next video on this screen looking at reflections. You should probably copy this into your notes and then get started on the next video to finish the lesson.